Okay, first of all, thank you for having me here to represent the InSAR community and our contributions to EarthScope. I'll be mainly discussing the past, present, and future plans in the InSAR community, the U.S. InSAR community mainly. And there are a lot of topics on this first slide, so why don't I give you the main points of the talk, and then we'll get through all the details. So basically, I'd like to say the InSAR community in the U.S. is thriving. Although we don't have our own satellite, we have support from UNAVCO and the Alaska Satellite Facility and funding from NSF and NASA, and we're doing quite well. We have our own organization called WinSAR, and I just checked, it's 14 years old now. And the main role of WinSAR is to gather or get data from foreign satellite sources, archive the data, and distribute it in a password-protected way, which is required by these foreign partners to our 80 or so WinSAR members. And then lastly, I'll talk about the satellites that are coming very soon. And this is really the future of InSAR, and we're almost to the promised land that we dreamed about in the late 90s. So the outline of the talk is here. I'll first talk about the original EarthScope Science plan from 2001, talk about how the fourth leg got chopped off, and then a little bit about how foreign satellites have come to the rescue, and how we've managed to keep going. A little bit about the strengths and limitations of the old InSAR satellites, and then I want to talk about the next big improvement that's coming real soon from two foreign satellites, Sentinel-1 and ALOS-2. Then mention the L-band, U.S. L-band mission that's possible before the end of the decade. And then finally, the most important thing is this to-do list for the U.S. InSAR community. What do we need to do to maintain access to these data sources? So everyone in this room knows all about EarthScope, the first three parts of EarthScope, but the fourth part, which was actually included in the original proposal, never really got off the ground. And I'll explain what happened there if you don't know the history. Here's a page out of the EarthScope original planning document, and the plan was to have a synthetic aperture radar interferometer to measure crustal deformation at millimeter sort of precision over all terrain types. And what we needed was a dedicated L-band mission to provide continuous coverage. We thought about 200-meter spatial resolution and 8-day temporal coverage throughout North America, but actually over all the active tectonic zones. The NRC reviewed the EarthScope Science plan and recommended that the InSAR component be included into EarthScope. The main contribution, of course, would be from NASA, but NSF was also willing to put up a significant contribution to an InSAR component to EarthScope. So there was a proposal from an ECHO team, Bernard Minster, Howard Zebker, Paul Rosen, and others, and it was quite an excellent proposal, actually, but it didn't get accepted at NASA, and therefore this component of EarthScope basically got taken off the table for a U.S. satellite, and of course NSF couldn't put the funding in because there was no satellite to fund. Here's a slide that I like to show. This is Matt Pritchard put this slide together, and it just discusses what I'm telling you, that NASA declined the EarthScope proposal, ECHO proposal. We're relying on foreign satellites. NVSat, UNAVCO was able to work with people at ESA to really gather all the ERS and NVSat data for North America, which is really remarkable. I think we have the better archive than they have at ESA. The Alaska Satellite Facility was funded by NASA to get all the ALOS-1 data for both North and South America, which is really a remarkable thing. And then, but the bottom line is today, all those satellites are dead, and there are no InSAR satellites today for scientific use, although that'll change soon. So a little bit about WinSAR. This is the web page at UNAVCO. WinSAR was absorbed into UNAVCO maybe 5 years ago. It used to be at SCEC, and UNAVCO has done a nice job of taking care of us. We consist of about 83 universities and research institutes, mostly in the U.S. We have bylaws and executive committee and elections and so on. And we have access to the data from UNAVCO and ASF. And we have short courses and workshops, that kind of thing. So if you're interested in doing any kind of InSAR research, you just need to send a small email proposal to UNAVCO, and they'll set you up with an account, and that's just required by our European and Japanese partners who don't want the data to be completely open. So the objectives of WinSAR are to promote InSAR technology and science in the U.S., and this sort of reiterates what I've already said. We have in WinSAR the complete ERS and NVSat archive, a lot of data. A lot of it hasn't been looked at. And then at the Alaska Satellite Facility, they have all the ALOS-1 data, which is really a remarkable data set. It's gigantic. I couldn't get the numbers, but it's maybe 5 or 10 times bigger than what's at UNAVCO. And that one it really is underutilized. So I encourage people, if you're interested in any kind of InSAR work, to go to these archives and look at the data. So what are the strengths and limitations of the old satellites? And I'll briefly go through that. Of course, InSAR provides you with deformation for events, earthquakes, especially in areas where there's no GPS coverage. And this happened recently in Mexico. We had this El Mayor Cucapá earthquake, and it was just south of the border, and there was very little. I think there was one continuous GPS station and some campaign GPS data. So it enables you to look at faults around the world and compare them with faults in North America and so on. It's a wonderful tool for events. Oh, this is just a slide. If you need to do GPS in these areas, you have to go out and do the old campaign-style GPS, which is it's a lot of fun. It's not very efficient, but it's interesting and a good learning thing for all of us. One thing we've been learning quickly is how to work with these large data sets. And here's an example of some interferometry for the Maule, Chile earthquake. And there's 2 points here. One is that you need to assemble lots of data and get a good image of the entire earthquake. And the second is we're learning how to do ScanSAR interferometry. And this is actually helping us go to this promised land. ScanSAR interferometry enables you to have a much wider swath, about a 300-kilometer wide swath rather than a 100-kilometer wide swath. And therefore, you can sample the whole Earth in 3 times more frequently, and this gives us a better time series. That's where we're going. But ScanSAR is tricky, and it's only now that these space agencies are able to align the bursts of the ScanSAR in a way that you can do interferometry. So that's the big thing coming. It's a technology improvement. Some examples about volcanoes and so on. You've seen all these interferograms, Yellowstone and around the planet, different volcanic features, and it's really good at monitoring volcanoes. You need GPS and you need the InSAR. GPS gives you the really good time series, and the InSAR gives you the broad overview of what's going on. But again, what's new since ALOS is that we're able to let me step back. There's two types of radar systems. One is at C-band at 6 centimeter wavelength, and the other one's at L-band, 23 centimeter wavelengths. The C-band is a remarkable instrument, but it only works in areas where there's very little vegetation. It decorrelates after some period of time. So we'd all like to go to L-band, the longer wavelength, and that's where this ALOS Japanese instrument comes in. And by using L-band, you can image jungle areas and look at deformation over long periods of time. So this is something done by the Miami group looking at the Sumatra and Java volcanoes activity. I'll give you an example of what we're trying to do in California by using GPS and InSAR together to measure the seismic moment accumulation rate along the San Andreas Fault System. Of course, this is what we all want to do. But an important point, again, is that GPS is wonderful, but it doesn't have the spatial resolution, so we still need to fill in some of these gaps with InSAR coverage. The other point, again, is that the C-band interferometry works south of Los Angeles, but north of Los Angeles, you can't form long time span interferograms. You need to go to the longer wavelength L-band interferometry, and that's where ALOS came in. But the problem with ALOS is that you'll see that it has poor control of its baseline, and also we only had one look direction. So we're not quite there yet, but we're going to get there soon. You've seen these maps, GPS velocity field. This is a remarkable result from, decades of GPS, continuous GPS mostly coverage, and we can get all these data at UNAVCO. Here's a map showing the InSAR coverage from ALOS 1, and there are lots of data that need to be assembled to form an interseismic. So interseismic is more difficult than the coseismic or rapid volcano monitoring because the motions are very slow, and you have to worry about atmospheric errors and ionospheric errors and those kinds of things. And it turns out L-band InSAR is not very good at length scales greater than about 60 kilometers because of ionospheric problems and so on. But that's where the GPS comes in. So we have this perfect marriage between InSAR and GPS to image the San Andreas Fault Zone. Sort of as illustrated on this slide here, our approach has been to take the long wavelengths components out of the GPS data using a model. So we build models of interseismic deformation, filter those models maybe at 40 kilometers wavelength, and subtract that from the InSAR data. Then high-pass filter the InSAR line of sight data and combine that with the low-pass filtered model and come up with a better data set that includes all of these length scales to about 200 meters resolution. That's about how good you can do. You need to do some spatial averaging to get the noise out of the InSAR. So I think you saw this last night from Jiapeng Tong. He's been working on this, combining InSAR and GPS, and this figure does not do justice to this data set. You should really go to this website here, and if you're bored with my talk, go there, download this KMZ file, and you can zoom all around California and look at groundwater pumping and all kinds of little tiny details that you can see in this InSAR data set, stepovers and faults, a lot of detail. One of the more important details is to look at fault creep, because if you want to assess the seismic moment accumulation rate along the faults, the creeping faults are relieving a lot of that moment, and maybe they're less dangerous over the long term. But the question is, are the faults creeping at the full rate, or are they partially locked? And that's the kind of thing we can see with InSAR that you can't see with GPS, or the creep meters only give you the details right next to the fault. You want to go a little bit away from the fault to see if it's partially locked at some depth. So you can see this beautiful correspondence between the mapped faults and the interferometry creep zones. There's a small step over here at Parkfield is right here, where we're going from the non-creeping to the creeping section. Here's another part of the creeping section. There's another step over right here that you can see nicely. And then if you assemble all these data, you can get estimates of creep rate along these faults, and then ask the question, how much of the creeping section is partially locked, and then a bigger question, if there was a major earthquake, could it rupture through the creeping section? Something that people at SCEC have been discussing. So these are the kinds of things you can do with this interferometry. So we need more, and the reason we need more is there's two reasons. First of all, ALOS had a limited lifetime, but it also had an orbital characteristic such that the baseline, this is the interferometric baseline, was drifting with time, and this drift is not good for change detection. It's good for other things, but it's not good for change detection. So we would like to control the baseline within plus or minus 500 meters at this 0 point here, and then you could make interferometric pairs from all the data that were collected, rather than just these dots that are connected by the gray lines here. And that really increases your ability to do time series analysis with InSAR. The other limitation, of course, is ALOS only had one look direction, and from one look direction, you can't discriminate between horizontal and vertical motion very well. We need two, at least two. More would be better. And what we'd like to do is time series. And this is an example in the LA Basin where there are enough ERS images to do a time series. And when you do that with InSAR and make a comparison with the GPS, you can see that there are seasonal cycles that are in agreement. And so, and actually this is the biggest maybe non-tectonic source of signal in the GPS and in the InSAR. So we need to sample the seasonal signal pretty well. And in order to do that, we need to have maybe more than 12 acquisitions a year. We need this baseline control. We need two look directions. And the other thing we really need, and this gets back to Jeroen's talk, is we need automated processing of ScanSAR, time series software, and computer tools to do all this processing. So as a community, we're building tools. We have ROIPAC, we have this GMT-SAR, something I'm interested in, trying to bring InSAR processing into the world of generic mapping tools, which we all use. And therefore, when you install GMT, you'll be installing an InSAR processing system, and you'll have it on your desk right away. You won't have to go through a lot of special installation things. The people at Caltech are building a time series analysis toolbox, which is really interesting because the GMT-SAR or ROIPAC just gets you to the unwrapped interferograms. It doesn't get you any further than that. If you want to do more complicated processing and time series, you need to use these other approaches, SBAS and so on. And there's a nice tool that's been developed at Caltech. So the final part of this talk is what's coming soon. And there are two satellites, Sentinel-1, which is a C-band satellite from the European Space Agency, and then ALOS-2, which is the follow-on to ALOS-1 from JAXA, the Japanese Space Agency. And then So I'll go through those. These are very interesting satellites that are coming later this year. That's real soon, and I think they're getting us closer to the promised land of InSAR. So Sentinel-1, again, it's this follow-on mission to ENVISAT. It has more applications than just deformation. I think that's on the next slide. Yeah, here it is. So it's a follow-on. But the applications are in this order. And when you deal with satellite systems, this is an important point to consider. They're interested in monitoring sea ice in the Arctic, very applied things, looking at oil spills and so on. And surface deformation is down at number 5. And what that means is that when you task the satellite to do different things, you'll be down in the queue and so on. If there's a major earthquake, they'll probably go and task the satellite. But if you're interested in some volcano somewhere, and you may not get the data very often. So Sentinel-1, the mission facts, it's a C-band again. It has a 7-year nominal lifetime, maybe 12 years total lifetime, sun-synchronous orbit. And here's the important thing, the 12-day repeat cycle. The previous C-band satellites were all 35 days, so you couldn't get a data set more frequently than every 35 days, and more often it was months between acquisitions. And so this one has the ability to do 12-day sampling. It's scheduled for launch October 1st, and also it has this new ScanSAR capability, and that's where these space agencies are going. Everything's going to be ScanSAR. It's a little bit lower resolution, but it has more frequent acquisitions. We're going to have to learn how to deal with this data. We don't normally work with ScanSAR data as a community. So here's a plot of part of the acquisition strategy where they're going to collect data every 12 days. And this is really good for us. If you look at this, it doesn't get everything we want in North America, but it gets the tectonically active zones in these wide swath ScanSAR things. So this will be good, and if we get our act together and ask nicely, maybe ESA will also image other areas that we're interested in. And they've been very good at doing this. So the data availability is a bit of a question mark, and I asked about this, and UNAVCO and ESA have been in very close correspondence with ENVISAT and ERS, and so they know all about UNAVCO, and I'm hopeful that we can set up the kind of arrangement where the data are archived at UNAVCO, all the data we're interested in, and we have access to it, and that has worked nicely in the past. Okay, one more satellite. ALOS-2, it'll be launched late 2013, so that's also very soon. Notice its applications. Number one is disaster monitoring. Of course, the Japanese are interested in earthquakes and volcanoes. This satellite is really focused on Japan, but of course they're collecting global data sets as well. It has a 14-day repeat cycle, ScanSAR, interferometry, and so on, just like the Sentinel-1, but it's L-band, longer wavelength, so it'll work in these vegetated areas. It has 2 look directions, which is something else that we need. Now they've put together this basic observations scenario, and they want to image everything, all the world, vegetation, Amazon, everything, ice, and so you'll get less frequent measurements of the deforming plate zone of North and South America, but it'll be okay. We'll get maybe 10 or 12 images a year from maybe both directions, and so it'll be good. whether or not we can get the data. They're clamping down a little bit more on their ALOS-2 satellite. ALOS-1 was more open. ALOS-2, they want to make it more commercial. But they did have an announcement of opportunity, and we had more than 50 proposals approved from U.S. investigators, which is good. WinSAR helped sort of put together all the proposals, and Chris Crosby from UNAVCO, I think, is on every proposal. And so our plan is to try to get the data into the UNAVCO archive somehow. It'll still be password protected, but we're trying to get it in there. Oh, and then finally the L-band mission from the U.S. It's on the drawing board. Its number one thing is to do displacement measurements, and I'll quickly go through this. They hope to have it launched before the end of the decade, so it's out there, and it would be really good to have this in the U.S. because not only would it be a super instrument, but it would help open up access to these types of data. They've been closed mainly because the U.S. hasn't been leading this effort, and so this would be a good thing for EarthScope to get behind, maybe for the next EarthScope proposal. So finally, the to-do list for the U.S. InSAR community. We really need to work with ESA to try to open up access to the Sentinel-1 data, and I think UNAVCO would be good at doing this. They've done this in the past. We need to work with JAXA to get these data sharing agreements, promote our NASA L-band mission, and then we can use all that to develop this integrated GPS InSAR model at high spatial resolution and better than seasonal temporal resolution. That's sort of important because we want to at least take the seasonal part out so we can go to smaller, higher accuracies. And then finally, we need to continue developing open source software and work with the ScanSAR data. So thank you.